welcome to the Classics of Immunology Journal Club. And today we have a special treat because we have a paper that was published, actually, can you believe it, 37 years ago by myself and Ellis Reinherz, who is with us today. And Ellis, say something. Say hello to the crowd. There you go. Okay. So the authors of this paper are Stefan Moyer, Rebecca Hussey, Doreen Cantrell, James Hogden, Stuart Schlossman, Kendall Smith, and Ellis Reinherz. This paper was submitted on November 3rd of 1983 to the Proceedings of the National Academy of Sciences, and it was published in March of 1984. And these dates are very important because 1983 was sort of the year that the lid was blown off the molecular nature of the T-cell antigen receptor complex by Ellis Reinherz and his crew. The title of this paper is the triggering of the T3-Ti antigen receptor complex results in a T-cell proliferation through an interleukin-2 dependent autocrine pathway. Now that's a mouthful, but basically what we're saying is that now we've cracked open how the T-cell receptor functions essentially and causes an activation and a proliferative expansion of the T-cells, which is really the sine qua non for why vaccines work, because the population of antigen selected cells then gets expanded. So that the second time around, if you get exposed again to coronavirus, you'll have a whole army there waiting for the coronavirus to invade into your milieu. The background on this paper is that these experiments were conceived in a collaboration that took place in August of 1983 when Ellis and I roomed together at the International Congress of Immunology, which was in Kyoto, Japan. And we just basically, when we weren't carousing, we were talking science nonstop, and we were sharing back and forth the results of experiments that we'd both done in our respective labs and so forth. It looked as though it looked to Ellis like the T-cell receptor was obviously very important for T-cell activation. And I also chimed in that the interleukin-2 receptor interaction was also very important. And we resolved to look into this whole, whether or not there was a cooperative interaction between the T-cell receptor and the IL-2 and the IL-2 receptor. Ellis's group had accumulated a whole bag of tricks of both molecular reagents and cellular reagents that nobody in the world had. He had multiple human T-cell clones, both T4 as well as T8 clones, and cytotoxic clones as well as helper clones. And he had generated monoclonal antibodies reactive to each of the clones, so that what he called then clonotypic antibodies, clonotypes as opposed to isotypes of immunoglobulin molecules. And he had shown in several papers that came out in 1983 that this was the antigen receptor complex. And so in my laboratory, we had also purified IL-2 to homogeneity. We developed a monoclonal antibody to the interleukin-2 molecule, used the antibody then to purify interleukin-2 over affinity columns. We generated radio-labeled homogeneous purified interleukin-2 and developed a binding assay for the interleukin-2 that would bind to the cell surface. We generated a monoclonal antibody reactive to the interleukin-2 receptor in collaboration with Tom Ullman's group. So we basically had a very, very unique, both cellular and molecular reagents. We decided to do these obvious, what were obvious experiments to us. And in the introduction, and I should say at the outset, Ellis's group did the majority of these experiments, and they basically wrote the first draft and wrote the paper, and we kibitzed on the sidelines and so forth. So in the intro, they lay out what was known, and what they said was that recent studies had shown that the T-cell receptor complex consisted of a clonotypic 90,000 Dalton heterodimer of 43, 49 kilodaltons, And also at the same time, there was a monomorphic or a common molecular complex that was called T3 at the time that was present on all T cells. So we had clonotypic molecule of 90 kD and a T3 complex that was about 20 to 25 kD. And later on, it was found to be composed of several subunits. And they had shown that binding on to using either anti-Ti, a clonotypic antibody, or monoclonal anti-T3, that it would lead to the loss of the surface molecules that these antibodies recognized. They would just go away. And I think at the time that most of the studies, and Ellis, you can chime in on this if you'd like, that they were either internalized, the antibody caused the surface molecules to internalize or to come off the cell surface. Do you know which one of those two or both of them were happening?
Both, really.
Yeah, okay. And so that happened within a few hours after if you left the cells at 37 degrees in the presence of the antibody, you would lose the expression, and that was called modulation. At the same time, they had shown that if you did this manipulation with soluble monoclonal antibodies, either to the clonotypic structures or to the monomorphic structure T3, that the cells would become hyper responsive or more responsive to interleukin 2 if you added interleukin 2 to the cells. Sort of analogous to antigen activated proliferation. They would proliferate to a much greater extent than if you hadn't added the IL-2. And therefore, the question that arose was really, so what's causing the cells to proliferate? Is it the T cell receptor, T3 complex? Or is it interleukin 2, or is it both, or really what's going on there? And we felt that we could attack this problem because we had generated all the critical molecular and cellular reagents. And therefore, we sat down over coffee in Kyoto and decided which experiments needed to be done, and then who was going to do all the experiments and so forth. And so from my lab, it was Doreen Cantrell was the principal person that was conducting the experiments at my lab. And I think it was a combination of Stefan Moyer and Rebecca Hussey and so forth in his lab, but you can modify that if you want. In the materials and methods, they delineated the human T cell clones that they used for these experiments. One was called CT3-Ti, and the other one, another cytotoxic, and another cytotoxic clone called CT4-2, and then an antigen specific. Those both were cytotoxic for alloantigens, and the cells were activated in an MLC and then placed in IL-2 and then grown up and cloned and so forth. The antigen specific clone was detects the presence of ragweed antigen pollen antigen. And it was a CD4 or a T4 positive clone, and it would become activated in the presence of antigen and in the presence of class 2 MHC that was autologous. And those cells, then they had shown, would become helper-like cells and help B cells. B cells were always a little bit slow as far as they needed to be told what to do, and help the B cells produce and secrete immunoglobulin. They had immunized mice with the clones, those 3 clones, and generated 3 different clonotypic monoclonal antibodies that recognized the 90 kD surface structure. And we had, in collaboration with Tom Waldman's group, defined that anti-TAC from their group would block IL-2 binding to the cell surface with our binding assay. And we'd also generated monoclonal antibodies reacted with IL-2 that we had used to purify IL-2. So the experimental assays that we used were basically just the proliferation assays that were performed in 96 well microtiter plates. In the presence, we would assay or monitor for proliferation or the duplication of DNA with tritiated thymidine. And for IL-2 production, we used our bioassay. The results are shown in table 1, and I want to use the screen sharing at this stage of the game, so I will turn that on. So this is table 1, and it's, as it says here, the in vitro proliferative responses of various clones to the IL-2 after modulation of the clone with the clone-specific monoclonal antibodies. And so this is the CTA3, CT42, and the ragweed antigen-specific clone. And if you just took the clones and unmodulated so that you didn't add the activating antibodies, the thymidine incorporation here was with just medium alone was 124 counts per minute, and with IL-2 was 3,300. And anti-TAC, the anti-IL-2 receptor, would markedly decrease that. Anti-IA, on the other hand, would not. DMS1 anti-IL-2 wasn't tested in this experiment, but then you can see here in the anti-T3-Ti modulated, you went from a low background of 560 to 7,000. Anti-TAC really brought it down. Then anti-IA did not change it, but the anti-IL-2 antibody did. And so this was about a 90% reduction with anti-TAC and only about a 60% reduction with the DMS1 antibody. Same general thing with the CT4 clone, marked increase, completely ameliorated by anti-TAC, and then but not anti-IA, and then DMS1 brought it down. And the same general pattern here in the antigen-specific CD4 positive clone. Figure 1 shows, and we go on to that, is the flow cytometric changes in different clones here. And I got to get my cheat sheet here so I can remember what all the things are here. In row A is medium alone. So that's just the clones assayed for T3 expression, T4 expression, T11 as a pan T cell marker, and TAC expression. And then in B, the cells were activated or modulated with anti-Ti. And so you can see that T3 goes way down. And so the clonotypic brings down in C is the antigen plus MHC autologous macrophages. And then in D is tetanus toxoid as a control antigen. And then in E is allo MHC. And so the thing is that what you can see is the T3 goes down, T4 does not, T11 does not, anti-TAC goes up. So the IL-2 receptor goes up. And the same thing happens with antigen and macrophages. And then if you look over here at table 2, you can see they quantitated the amount of surface expression through the fluorescence intensity and so forth. And this is now the antigen activated clone. T3 molecules with medium alone is 45,000. Anti-Ti brings it down, and antigen and MHC also brings it down. Whereas, and so these means that they were modulating the T3-Ti complex. T4 antibodies don't do it, T11 antibodies don't do it, and the IL-2 receptor, while these go down, the IL-2 receptor goes up. So then if we move on to table 3, which shows us IL-2 production and blocking of proliferation by monoclonal antibodies after antigen receptor triggering, we've got stimulation of clone CT8 and the antigen-specific clone, CD4 clone. And now we have stimuli here. So this is the alloantigen. LAS156 is the name of a B lymphoblastoid cell line. And now we have the clonotypic antibody, not soluble, but rather bound to activated cephalose. And here we have the anti-Ti soluble. And so if you look then at IL-2 production, with soluble anti-Ti, there was basically no IL-2 production. Whereas with the alloantigen, there was IL-2 production, and with the anti-Ti cephalose, bound to cephalose, then the cells made IL-2. And then if you looked at the thymidine incorporation, the proliferation of these cells, with medium alone, there was 29,000, and anti-TAC inhibited that, as you'd expect. So did anti-DMS1, but not as well. Anti-T3-Ia did not. So that's just like what we showed you in the last couple of tables. With anti-Cephalose, anti-TAC brought it down, DMS1 brought it down, and anti-A didn't. And whereas if there was no IL-2 produced, there essentially was no proliferation. And the same thing, the same general thing happens with the antigen-specific clone. Those were the data. In the discussion, the very first, the last figure of the paper and the first part of the discussion was this schematic that actually Ellis's group, his cartoonist, put this together. And so what we've got here in schematic form is a summary of what all those data were. And so we have a macrophage here and presenting antigen, which is the little triangles, and activating the T cell receptor, which is just a V on the surface of the T cell. And then also these are monoclonal clonotypic monoclonal antibodies here, and they're activating the T cell receptor also. So you can either activate them here with Cephalose bound anti-Ti or T3, or you could do it with macrophages and MHC peptide complexes. And so if you activate the cells, what happens is they lose their T cell receptors. I should have shown you this up here. These are the T cell receptors here. So they start to lose, they're modulated. And then what happens is the cells start to spew out interleukin-2, which are the little round circles. And the interleukin-2, you can see that there are arrows on here. They're basically an auto-stimulatory situation whereby the IL-2 that the cell is making is coming back and binding to the IL-2 receptor. And that causes the cell then to, and here they're all occupied in this cartoon, that causes the cells to undergo DNA replication. And this cell is in the process of undergoing mitosis into two daughter cells in numbers 1 and number 1. So that's it. And I'll stop the screen sharing here now and come back to Ellis and myself. And so in the discussion, this summary of the results that I just showed you, was the conclusions were that there was a functional linkage between the antigen receptor and IL-2 production and proliferation. Okay, and that soluble anti-Ti, the clonotypic antibody, or T3, caused an increase in the number of IL-2 receptors, but not IL-2 production. So clearly bound to the surface of the cells because it modulated the structure off the cell surface, internal or external or both, but it didn't cause the cells to activate IL-2 gene expression. Whereas if you bound the anti-clonotypic or anti-Ti T3 antibody to the Cephalose beads, then you would get IL-2 production and IL-2 receptor expression and proliferation. You get the whole ball of wax. So we felt at that time that this supported the interpretation. Well, Ellis felt that this further supported his quest to demonstrate that the Ti molecule and the T3 molecule were really actually parts of the T cell antigen receptor complex. There's somehow information is being transferred from the antigen to the antigen receptor to the IL-2 gene and IL-2 receptor genes, and that sets the whole thing going. And so I have some questions for Ellis about this whole thing that we've talked a little bit about before this presentation. And so I wanted to know what's the difference in TCR activation between a soluble anti-clonotypic antibody or a solid phase anti-clonotypic antibody? Can you tell us about that?
Sure. Before I tell you about that, however, I wish to point out that all three of these clones derive from myself. And I'm saying this because I was the only one willing to give blood frequently enough that this made it possible to do. And the second point is in those days, we were allowed to do that. There weren't all these HIPAA rules, et cetera. And the third point, which is perhaps the most relevant, is the ragweed E specific clone was derived from me, since I have a rather wicked allergy to ragweed E. And this is manifest as hay fever every spring. And I never found use for that allergy until we made this cell for me, which was really quite remarkable because, as you said, it was CD4. It was induced by ragweed E antigen on my antigen presenting cells with my class 2 MHC molecules. And it induced B cells to make antibody, and including, and in particular, IgE, which was the basis for my allergy because it was loading up mast cells. And then whenever ragweed was around, it would waft through the air, land in my mast cells, and cause them to degranulate and give me runny noses and eyes that itched and so on and so forth. But to your question, anti-clonotypic antibodies, the so-called anti-Ti antibodies or anti-CD3 antibodies to the constant region subunits of the T cell receptor, when they're used, you can only get a bivalent interaction, right? It says each immunoglobulin molecule of those monoclonal antibodies has 2 arms. And so each monoclonal could just bind to 2 things. So that gives you a little tickling of receptors, but doesn't give you enormous cross-linking that is bringing together of many, many different receptors. And that's what Cephalose beads do. They allow you to put a large array of these antibodies on the surface, and they're physically linked on a surface. So by definition, when that bead with the antibody comes in contact with the surface of the cell, you aggregate many more receptors together. And the simple notion is that you start engendering a strength of interaction and a locality of interaction because of the cross-linking on beads, as opposed to just having different points of contact by 2 bivalent arms of a single antibody all around the cell surface. And of course, it's now known that T cell receptors like to aggregate. They do so when they confront antigen bound to MHC molecules on an antigen presenting cell at a surface. And this starts to stimulate what we know to be myosin motors and things that are attached to the T cell receptor. And then through the cytoskeletal motions, bring all of these together naturally. So
can I ask another question? So you've proposed, you have data out there more recent than 37 years ago, right, looking at how this T cell receptor works, and you've come up with a concept that the T cell receptor is a mechanoreceptor. So can you tell us what a mechanoreceptor is and how it fits in with this idea of the soluble antibody versus the solid phase antibody and triggering?
So this is slightly complicated. Let me just start with the description of a mechanosensor. So normally when you have a receptor ligand interaction, it occurs at thermal equilibrium. That's what you measure when you look at IL-2 receptor interaction, a classical receptor interaction at thermal equilibrium, or antigen antibody. But the T cell receptor doesn't work like that. It works far from thermal equilibrium, actually, so that when force is applied to the bond between a T cell receptor and its ligand, a peptide molecule bound to MHC, as force is applied to that bond, the bond gets stronger. That's in contradistinction to what happens with antibodies. In the T cell receptor, this phenomena and is known in other receptors as well outside of the immune system. But in the T cell receptor case, this is referred to as a catch bond. Think of putting your finger into a Chinese finger puzzle, you know, one of those thingamabobs that you get. You put your finger in, then you try to take it out. And the more you pull, the harder it is to take it out, right? That's a catch bond. A slip bond is the binding is strongest under no force, and as you apply force, it slips away. So the whole system works differently. This, in structural molecular terms, the T cell receptor catch bond is a consequence of a structural transition. The T cell receptor goes from being very contracted to actually it elongates, and then it goes back down and it oscillates like so, even when it's bound to the same ligand. And that oscillation is very important for putting energy back into the membrane. And it does so, which then affects all the lipids in the vicinal area and allows the cytoplasmic tail to dissociate from the inner leaflet of the membrane of the T cell so it can become accessible to phosphorylation by a kinase like LCK and other things that go on and lead to the activation process.
So would you say that the soluble antibody doesn't form the catch bond, but the solid phase antibody does form the catch bond?
Well, so, okay, yes. In other words, what happens is that when you've got a surface and you have things linked to it, you can generate forces between the molecules. So what you're really doing is one is a pivot point and the other is a force that can be applied between two structures. So it's not quite the same as what you do when cells are moving. So normally T cells are interrogating their surroundings, so-called immune surveillance. They can do this through the blood into the lymphatics, or they can do this actually if they're stuck in a particular tissue, like lung, for example, during a lung infection or whatnot, and they may live and reside in that place, but they move around locally to see if they can contact antigen or if antigen's there. And they're constantly sweeping the surface of other cells, epithelia or what have you, looking for their ligands. When they see the ligand as they're moving, if it's the correct ligand, that motion provides the force that then generates the catch bond. Okay, so that's normally how it works. And then once that catch bond occurs, then you get this mechanical property I'm describing to you with the motion of the TCR back and forth. That in turn leads to activation of cytoskeletal motors, which come because of a calcium flux change, activates those. And then you get T cells moving together, not just the T cell receptor that's been activated by the catch bond, but other T cell receptors which have not been ligated are also moving into that area. So that's how you form what's called an immunologic synapse. Now, T cell receptors, one from the other, even if they're of the same specificity, you may have 300 different ways that T cell receptors could see a particular peptide MHC combination. So 300 different, literally, clonotypes, which differ in terms of their sequence and so forth, will see the same thing. But they don't behave in the same way. They have different force requirements. And so the catch bond forms more strongly at different forces under different circumstances. And a lot of this is predicated on the requirement to have a repertoire that's large enough to allow for T cells to work in one environment where the system is much less compliant. For example, an inflammatory circumstance that could be around an epithelium because you've got tight junctions between the epithelium, so it's much less compliant. That can shift the dose response curve substantially and so forth than it would be in some sort of tissue which has lots of compliance where things can work, such as blood, for example, where things can work at a lower force bond lifetime response and so on and so forth. So the system is really highly tuned. Now, when we do these experiments like we did 37 years ago or whatever, we were using antibodies as crude tools to elucidate the fundamental process that this kind of cross-linking, which does relate, as you said, to mechanical forces and so on Cephalous beads, works. The anticlonotypes only work because they're clone specific to stimulate that specific clone. So an anticlonotype to clone A will stimulate A. It won't stimulate B, C, D, and so on. Anti-CD3 being the same on all clones because it's the signaling components of the TCR complex will work on clones A through D and then going down the alphabet. So this is the sorts of things we were looking at that time. And then with the wonderful reagents you had to interrogate the IL-2 receptor system, I think for the first time, we were able to really demonstrate that there was this direct linkage between antigen receptor, the T cell receptor, interaction with peptide MHC, and then what you refer to as the hormonal system that gets turned on as a consequence of that TCR triggering to first induce IL-2 receptor, which seems to be easier to do because you can do it with an anticlonotype in solution alone, and then a more robust interaction that is required to generate induction of interleukin-2. So you get this loop of autocrine production of the IL-2 and the T cell that's now receptive to bind its ligand because you've upregulated the IL-2 receptor. So
let me interject it right here at this stage, because in terms of activating the IL-2 receptor gene, in this instance, we were monitoring for the alpha chain of the IL-2 receptor, which we called TAC antigen. And a few years later, after we published, you and I published this, it was shown that the NF-kappa B is the transcription factor that's important for the initial TCR-induced activation of the alpha chain, IL-2 receptor alpha chain expression. By comparison, in order to get IL-2 gene expression, we have to activate 3 different transcription factors, NF-kappa B on the one hand, and then NFAT, a nuclear factor of activated T cells on the other hand, and then AP1 as well. And Ellen Rothenberg has shown that you have to have all 3 of these transcription factors glommed onto the promoter region of the IL-2 gene in order to get it activated. And if you can use pharmacologic agents to take one of them away, for example, and then the whole complex falls off, and then IL-2 production stops. And of course, we were the first ones to show the way to manipulate that pharmacologically with glucocorticoid hormones. And then subsequently found that they stopped the participation of NF-kappa B into that complex and so forth. So it seems to me, so that the one point to make, I think, is that as far as I know, the TCR is the only receptor in immunology that's using a mechanoreceptor kind of a mechanism. Is that correct?
Well,
in the immune system.
Integrins do this kind of thing as well. I mean, they have catch bonds that can form and can be regulated. I think one thing in that regard worth noting is that when a cell is moving, and that's an integrin-mediated process, you're generating forces that are in the nanonewton range. Okay, 1 Newton is the force generated by an apple falling 1 meter, basically, to give you an idea, if you think about a Newton. So we're talking about, with T cell receptors, piconewtons, about 10 piconewtons.
1,000-fold less.
Yes. So basically, the force to do the mechanotransduction is just coming because the T cell receptor is using some of that good force derived from the integrin ligand interactions to mediate the motions of the T cell, and just simply using a very tad amount of that to do its thing. So it's really kind of a remarkable system, and it's all linked to the motion of T cells on the one hand, the external forces, they're going along surfaces, and on the other, retrograde flow of actin internally from cytoskeletal motions and so forth. And so the T cell receptor functions more or less like a Segway. So if you're on a Segway, if you go forward like this, you're pulled back like that, right? So when the T cell's moving and you get a force applied this way, the retrograde flow is in the other direction. So what happens is the system's really nicely tuned so that the T cell receptor wants to stay in its sweet spot of about this 10 piconewtons. And if it didn't do that, then you wouldn't get this nice resonance and other kind of phenomena that are important in the process. The point I wanted to mention, though, also related to something historic, which you said, is that when we began these experiments or thought about these experiments, it was in Kyoto, and that is correct. I stand by your statement as far as that is concerned. However, my recollection of this was that our discussions that were actually substantial mostly occurred late at night and drinking Japanese whiskey as opposed to breakfast. I don't know whether you cleanse for your viewers or what, but that's my recollection of this. In any event, the other thing I wanted to add toward that point is that we ended up going to meetings together because we were dealing with receptors. And so there was always something about T-cell receptors and always something about interleukin-2. And my recollection of those meetings was that you were always telling me that the IL-2 receptor was much more important than the T-cell receptor and vice versa. So that's how we ended up doing these experiments. And then that truth was somewhere in between, that they worked together.
No, I think that's, you're right. No, you're right on with that. And one of the things that reminds me, I wanted to say with regard to the IL-2 receptor interaction, in contrast to this mechanoreceptor concept, which is, the more I hear you talk about it, the more complicated it gets. But in contrast, the IL-2 ligand receptor interaction obeys the law of mass action. So as you raise the concentration of the ligand, you get to the affinity of the receptor dictates whether or not the ligand will be bound or not bound. And then it's an on-off kind of thing. It's constant and a very dynamic process. And what we showed in our experiments, actually the Doreen Cantrell experiments that I discussed last week, that there's only three things that you have to worry about. One is the ligand concentration. The other one is the receptor concentration, or the receptor density on the cell surface. And then the length of time, the duration of time that there is an interaction between these two things. And these are the classical characteristics of hormones and hormone receptor interaction, established 50 to 100 years earlier by the endocrinologists. And that's why when I figured that out, or when we realized this, that's when I got on the soapbox and to say that the way the immune system is working is that it's taking an external signal from the antigen that's coming invading from the outside into the internal milieu. And then once that happens, the IL-2 receptor deal takes over. So the antigen receptor isn't necessary anymore, because now the whole thing is internally regulated. And what I found when I started spouting off like that in different venues, the immunologic community had a lot of trouble with that, still do. And I don't think anybody really ever realized what I was trying to say. What do you say to that?
I think that most rational people had to have come to the conclusion that IL-2 receptor working downstream of the TCR initially really becomes very important, not just as part of a general mechanism, but also in terms of induction of all kinds of programs that are telling the cell what to do in the future, whether it's linked to memory functions or effector functions and a host of things like that. So I think most people would believe this in this day and age.
Really? You think that?
But much more is getting nuanced now as people are really digging deep into, transcriptomes of cells and being able to define what all the genes are that are turned on when, and all kinds of epigenetic phenomena that are also linked to interleukin-2 actions, as well as TCR interactions, and showing how they synergize and whatnot. So I think more and more people are coming to recognize this. And I believe from a pharmaceutical industry point of view, people are also recognizing the fact that interleukin-2 could be modified in some ways so that it helps direct a particular kind of response, not just to proliferation, but also to its important differentiative components. So, you make some pharmacophore that really is important at inducing T-cell memory and so on. So I think the next generation of iterations that are going to come along and take advantage of the biology that was described 37 years ago. I mean, we certainly didn't describe it all, but we provided an important starting point to show the relationship between T-cell receptor and interleukin-2 receptor. I think this is just going to get better and better, become more nuanced, just as, you know, the ideas we had back then of what a T-cell receptor was, we certainly had no anticipation until, you know, well into the 2007 and thereabouts, that there was a mechanical force relationship. But it, yeah. So
yeah, no, I agree. Well, I think that's great that we have you on the record now for saying what you just said. This is an advance for immunology, I figure. And so I don't have any more questions. And so let's stop on that note. And we should do this again sometime. So yes. I forgot to say in the very beginning of this that if you like this video and you like the Journal Club, don't forget to go on the YouTube channel and click on the like it, and then click on the bell to get notified for more. And go to my website, scroll down, go to my website and find all the classic papers of immunology. You'll find all of Ellis's papers there. Well, maybe not all, because it goes into the hundreds, but a lot of them are there. So, hey, thanks so much. It's been great. And thank you, Ellis, for taking a time out of your busy schedule and to talk about these issues.